This lecture will briefly highlight some of the concepts from Chapter 2, Defining and Measuring Energy. I want to make sure and review the idea of the bomb calorimeter. When we're determining the amount of energy content of food, essentially this is what's used to figure that out. If we're looking at this diagram right here of the bomb calorimeter, we can see that the food is placed right in here in this mechanism connected to the heating element. Essentially, the food is burned to ash, and the heat emitted from burning that food is measured in the water change of the bomb calorimeter. The thermometer measures that water change. The insulated container keeps the heat from escaping, and by that change in heat, we can determine how many calories or how much energy in calories is produced by that food. When we're looking at what's produced from the bomb calorimeter versus how humans metabolize the energy in food, we can see that there is a difference. Carbohydrates produce about 4.2 calories per gram in the bomb calorimeter. Pretty similar in humans. We can pretty much metabolize carbohydrates and get all the energy from there. Fats are about 9.4 in the bomb calorimeter. Humans, 9.4 as well. Proteins, this is where it differs. In the bomb calorimeter, proteins produce 5.7 calories per gram. Well, in the human calorimeter, or our bodies, we can only get 4.2 calories per gram from proteins. We can't metabolize the nitrogen on the proteins for energy. So in the bomb calorimeter, that can be burned and that energy harvested, but that isn't the case in humans. And then finally, for alcohol, in the bomb calorimeter and in the human calorimeter, they're both 7 calories per gram. So you might notice that some of these numbers sound kind of familiar. We know that carbohydrates provide 4 calories per gram, fats provide 9 calories per gram, proteins provide 4 calories per gram, and alcohol provides 7 calories per gram. We can see that those have been rounded down. Essentially, when we think of calories in food, when we think of energy expended, when we think of determining our resting metabolic rate, all of those are estimates. There's always going to be some error in this. We can have more reliable estimates and measurements in some methods of determining. I apologize, that was my dog shaking. We can have some methods of estimation that's more accurate than others, which we'll go through next. But essentially, this is how we're determining the energy that food provides, and then how we can metabolize that food. When we're determining the amount of energy expended in humans, we can do that via something called direct calorimetry or indirect calorimetry. Direct calorimetry is measures of estimating or determining the energy content expended by changes in thermal or heat energy. Indirect calorimetry is used to measure the changes in oxygen consumption and or carbon dioxide production. Direct calorimetry is going to be more reliable, more accurate than indirect calorimetry. An example of direct calorimetry is the bomb calorimeter. In addition to the indirect calorimetry, a less reliable way of estimating the amount of energy expended is through some of our metabolic measurement or estimation systems. We will go over those in just a minute. And these do include some methods of measuring this, but then also I'd like to include that we have estimation equations. They're not part of the direct calorimetry or indirect calorimetry, but we still use them to estimate energy expended. And as I mentioned, they're going to be your least reliable. This example right here is a whole room calorimeter that might be found in a laboratory research setting that has a capability to do direct and indirect calorimetry. For direct calorimetry, again, measuring the heat change, the room is equipped to be able to measure the heat production of this individual as he cycles or as he exists in this room. In addition, the consumption of oxygen and the production of carbon dioxide can be measured for it to be indirect calorimetry. And again, this is mostly in a laboratory or research setting. It's very hard and expensive and rare that we find direct calorimetry as a method used. This picture is of indirect calorimetry. We can see that there's a mask over this individual as he cycles. This device is often called a metabolic cart. Again, it's measuring the oxygen consumption and carbon dioxide production to determine the amount of calories expended. This picture here shows a very similar setup. Again, somebody with their nose and their mouth covered, a tube connected to the machine, but the difference here is that this individual is resting. He's fasted, he's rested, he is essentially in the process of determining what his resting metabolic rate is. Whereas the picture previously, we were measuring the energy produced or needed during an exercise activity. A little bit of a less reliable method is something called the MedGem. You can see again this individual has her nose plugged. She's breathing into the machine and it's doing the same thing. It's measuring oxygen consumption, carbon dioxide production, and based on that can determine how many calories are expended. The advantage of this is that it's portable. It's less expensive than some of the other items. We have this item at my office currently, and when we use it quite often. Well, some of the other indirect calorimeters, the metabolic carts, might be found in more clinical settings. I think there's a couple locations or one location in town that does have it in a gym or fitness facility. An example of a portable metabolic measurement system is here as well. It works similarly to the MedGem, again, indirect calorimetry, but you can see that this individual has it on their back, has a mask, doesn't need to use their hands to hold it up. So this can measure the amount of energy expended during an exercise activity.